Alright, so this is we're going to start looking at rotational dynamics. And the first thing we want to look at is Newton's second law for rotation. So we talked about how torque kind of acts like a rotational force. In fact, it can be thought of as a rotational force. If the sum of all the torques in an object is 0, that means the object is either not rotating or rotating at a constant angular velocity. What that means is if the sum of all the torques is not 0, that must cause angular acceleration for an object. And so we should be able to write an equation that looks very similar to Newton's second law, F equals ma. And what I've written here is sum of torques. Basically like the F, the force is equal to I, what's called the moment of inertia, times the acceleration, alpha, the angular acceleration. So what this I really is it's a way to account for the inertia of the object. If we think of what inertia is, it's really the object's resistance to changes in its state of motion. In Newton's second law, mass is an object's inertia. A larger object or a more massive object experiences a smaller acceleration if the force stays constant. And here, we call this moment of inertia. It's a little bit more complicated than just the mass of an object for rotation. But let's actually do a quick example problem first, and then we'll go back to looking at moment of inertia in a little bit more detail. So here we have an electric saw motor, and we have a circular blade. It's going to go from rest to an angular velocity of 80 revolutions per second and 240 revolutions. Tells me the moment of inertia of the blade, 1.41 times 10 to the negative third kilogram meters squared. And it wants to know what is the net torque the motor has to apply to the blade. First step that we want to do is figure out what the angular acceleration of the blade is. Here are the 4 things that I know. Probably what I want to do is get both my final velocity and my displacement into radians. Easiest way to do that is multiply by 2 pi, because there are 2 pi radians in a revolution. And now I can figure out alpha, one of my 2 unknowns. So the 2 relationships I'm going to use, torque is equal to I times alpha. If I figure out alpha, I can just do I times alpha. And I'm going to use 2 alpha times theta is equal to omega initial squared, plus omega initial squared is equal to omega final squared. So I do some algebra. I'm going to solve that one on the right for alpha, subtract initial angular velocity, divide 2 times the displacement. And then I'm going to take and substitute it in right there. And so I get torque is equal to I times the quantity, final angular velocity minus initial angular velocity, those 2 squared, divided by 2 theta. If I plug in to do my math, I calculate the torque has to be 0.117 Newton meters. Now, if I knew how large the blade was, we could maybe figure out some things about the forces that are acting on that blade. So, to start to talk about this moment of inertia piece in a little bit more detail, what I will do in class is a demonstration that I call the Great Race. Hopefully I've already done it in class, but I'm going to have a metal ring and a wooden disc that happen to have the same mass and the same radius. And I'm going to release them from the same height up an inclined ramp which has the same incline for both of them. Which one gets to the bottom of the ramp first? Is it going to be the metal ring? Is it going to be the wooden disc? Or will it be the same? So when I do this in class, I'll ask you for your answers. Try to think about what is going to cause an object to get down to the bottom first. Now what actually determines this is, the answer to this question is this idea of moment of inertia. A measure of the resistance to changes in rotational motion. It really depends upon 3 factors. The first factor is the shape of the object. Is it a ring? Is it a disc? Is it a sphere? Is it a metal rod? Is it a rectangular metal plate? The second of those factors is, where is the axis of rotation? Is it through the center of the object? Is it about one of the ends of the object? Is it somewhere else in the object? And the third thing is the distribution of mass within an object. Is it something where the mass is equally distributed throughout the object? Is all the mass on the outside? Is all the mass on the inside? Now if we have a point mass, the moment of inertia for a point mass is just its mass times r squared, where r is the distance between the mass and the axis of rotation. For solid objects, it becomes a little bit more complicated. because what we need to do for a solid object is take and break it up into individual particles of mass, do mr squared, mass times the radius or the distance between that point of mass and the axis of rotation squared, and then add all those up. Luckily for us, that calculation becomes easy for some set of objects. One of them is a thin-walled hoop or cylinder, where moment of inertia is mr squared. One of them is the solid cylinder or disk, where moment of inertia is half mr squared. Solid sphere, either rotating through the center or thin-walled sphere through the center. A solid sphere which is rolling around something. And then we have some for rectangular sheets. Now, for those of you who are interested enough in physics to take AP Physics next year, I know that you talk about this in a little bit more detail, because this is a really cool example of where you can actually throw some calculus in there. So that's kind of the end of this lesson, looking at moment of inertia. What we'll do in the next lesson is start to look at some other ways that we can use this quantity.